Very much for the kind introduction and welcome everybody. Good morning. I'm Carlos Garcia from the University of Glasgow, and today I'm bringing a methane gas sensor. So for that, I want to highlight that this work belongs to one of my PhD students, McGann, the first author in this list, and that corresponds to a IEEE sensors letters that we just published through this great opportunity and initiative that they have launched this year. I have also to point out that Greg got a lot of support from our postdoc, Fleming, the third author in this paper. So the work that I'm presenting today, I'm totally getting them the credits that they deserve. So my presentation is divided in three main parts. In the first one, as you can see there, I will highlight the motivation, why we want to detect, in this case, methane. Why it's so important, especially this year in anthroposensors that we are encouraging people to bring sustainability technologies. This is going to be a good excuse for me to convince that detection of methane is a big thing nowadays. So for that, I will discuss what material we have selected. Of course, it's not the most eco-friendly material, and we are, in this case, proposing follow-up works, which are based on more sustainable materials. So we'll talk about that. And how we did it is covered in the second part. In the second part is band-gap engineering of this 4-6 material from the theoretical point of view and also from the experimental point of view. And that will be covered in the third part, where I show you how to do a sputtering, co-sputtering of this material, customizing the content of, in this case, cadmium and lead to adjust the band gap to the absorption band that we want, in this case, for the detection of methane. So let's go directly to the main message. So why do we want to detect methane? So there are 4, in this case, topics that I want to highlight that involves environmental, in this case, impact. As you can see here, I will just point to here, global warming, 25%, more than 25% is caused by methane emission. So detection of methane is critical in order to reduce the global warming and the climate change that we are, in this case, discussing in some of the events that we organize worldwide. One of them, as you can see here, people commit reduced, in this case, the emission of methane down to 30% by a certain date. That's a commitment from all the countries, especially in Europe. As you can see, the second one corresponds to the energy and industry leakage. That also has an impact in terms of the economy, because you reduce, in this case, the leakage, you detect, and you can save some money. You want to transport, in this case, methane from the industry to our houses, so you detect methane leakage, then you can. Agriculture, unfortunately, some of our animals, especially the beautiful cows in Scotland, they have a diet that they emit, in this case, livestock digestion, manure, in this case, decomposition. They emit a lot of methane, so we need to change a little bit the diet. I'm talking about killing animals. We are just changing to a more healthy diet in order to prevent that emission of methane. And finally, but not less important, to prevent any kind of active. If we reduce methane emission, that's one of the things that we will have a reduction of the increase of the temperature in the planet, 0.3 in this case, by 2040. That's kind of the expectation. So that's quite critical. How to detect methane? One of the things, in this case, in this list, you can see the 4 main gas detectors that are in the market or are under investigation in labs. I won't go in detail in all of them, but this is the one that we are investigating with within our research group, which is called Non-Dispersive infrared gas detector. So essentially what it does, it uses a light source that is infrared. You put, in this case, the gas in the cavity, in the chamber, and then you have a photodetector, which is also detecting infrared. So if the gas is absorbing the light emitted by the source, the detector will say. And there are some good theoretical predictions and experimental proofs that they detect, in this case, parts per billion. It's quite a selective method, as I highlight in the pros of this technology. The disadvantage is that it's just suitable for certain gases. So that's one of the, I would say, the cons that we have. But methane is one of them. So that's why we have explored. The configuration, the four main parts that we have, I will highlight it with a pointer. So we have an infrared light, a gas cavity, as I have highlighted, a filter, and then an infrared detector. In this work, what I'm bringing is an infrared source that can emit 3.3 microns, that it will, in this case, activate the molecule of methane. And we develop also in our lab, that will be for a follow-up work in the future, the infrared photo detector. So the combination of both systems will make the non-dispersed infrared gas detector. And we are working also in CO2, by the way, with different combination of materials. This is kind of the summary. You see on the left-hand side, you have the absorption band of methane. You can see that there is an abrupt peak that is saying that methane is, in this case, absorbed 3.3 microns. So that's why we need to really do band gap engineering to that specific band. How we can do it? Of course, we can select 4, 6, or 3, 5 materials. These are the candidates. I know that they are not eco-friendly as per the legislation nowadays, but this is what research we have on our hands. So we have lead selenite, and as you can see, lead selenite, it has an absorption of 4.59 microns, and then we have cadmium selenite, which is 0.729. So as you can guess, if we mix with an alloy, we can tune the absorption to 3.3. And that's what we have done in this work, theoretically and proof experiment. There is a work that is demonstrating that changing the cadmium content, increasing actually the cadmium content, can increase the band gap energy. So that was the first demonstration a few years ago that pushed us to try in our co-sputtering system. Before that, we need to do some calculation just to know how much % of lead or cadmium we need to put inside. What we have done briefly is to deposit some samples in our sputtering system with different content of cadmium and analyzing the optical properties, optoelectronic properties. So for that, we have done spectrophotometry to measure the transmission, the reflectance, and using tau, we calculate the band gap. We also measure the content using EDX, and then we plot the data. We see in this case almost a linear progression reproducing. If we increase the content of cadmium, then the band gap energy increase. So let's tune it into the 3.3 microns. Before that, we used, in this case, to calculate what is the pure lead selenite and cadmium selenite band gap, because this is needed. And we have discovered, in this case, with our calculation, these are the band gap corresponding to the pure binary components. Once we have it, we use the Bowen expression to calculate what is called the Bowen constant, 0.9 for our components. 0.9, it was calculated in this case, you see at the very bottom of the slide. Once we have calculated that, we put it in the Python script and we fit both of them. So that allows us, not just in this range, but in all the range that we have in the graph, in this particular case, the band gap that we want to optimize is the 0.37 that corresponds to pretty much 10% of cadmium. And that's, in this case, our goal in our sputtering system. That is the sputtering system. As you can see on the left part, I will use the pointer. We have 2 targets. So the system can work either with a pre-composition of a target content of cadmium, let's say 10%, and we do pulse DC sputtering of the target with that specific content, or we use 2 targets, one lead selenite, the second one cadmium selenite, and we play around the power, we play around the argon flow in order to optimize the content. One of the things that I want to mention here is, in order to get an infrared light source, we need to activate the material. And that's key for the work. If we don't activate the material, if we don't create acceptor levels in the material is not acting as a PL, photoluminescent source. How to do that? We did annealing, a diffusion process, a sensitization process using oxygen and iodine. That's kind of the key part, and we discussed this more in detail in the paper. In order to kind of do a short talk, what I can show here is where we put, in this case, our sample is in between LED that is pumping photons with, in this case, a certain wavelength, producing, in this case, the excitation of the electrons well beyond the conductive band, and then the non-radiative recombination to the edge of the conductive band will produce the 3.3 microns photons that we need for, in this case, for the methane to get excited. On the right-hand side, you see our setup for evaluating the PL, and this is kind of an overview of how it looks. So when we create the cadmium lead selenide samples, these are a good spectrum about how it looks, the material. One of the things that I want to highlight is, depending on the use of oxygen or not during the process, we see that the morphology change. And this is essentially a proof that we are, in this case, adding some defects to the structure that can produce that nice PL emission. The sample that it works nicely for us is the one that you see at the right bottom. In this case, you see that this it has been grown not just with oxygen, but also post-sensitized with oxygen and iodine. The last thing, this is kind of the main result that we saw in this paper. Our light source for the detector, they emit, and they only not emit, but they do it in a reproducible way. I mean, that 3 samples grown in different days using exactly the same conditions, they show exactly a sharp 3-point emission. That's what we need, and a very abrupt emission. Whereas if we compare with other works using evaporation, you see that the peak is changing every time that we repeat the process. So our process that I described before, and I'm finishing with this one, that is producing this emission mainly because it has that kind of oxygen acceptor created within the band gap. So that's kind of the key message that you need to remember. The last thing I want to mention before I conclude, because I'm running out of time, we use design of experiments to further optimize the emission of this sample. And that means we play around the thickness of the samples, the post-sensitization time, the annealing temperature. This statistical analysis allows us to save time samples while optimizing the PL emission from the samples. I think I pretty much covered the whole thing in the short presentation, but those are the main conclusions, where in red is highlighted the role of oxygen is key for the PL emission. At the very bottom, you can see the prototype of the product that we are developing, in this case in collaboration with Alba, which is a SME in Scotland. Thanks very much for your attention.